Hi class, this is number 5 on 10.1. Let me share my screen. A research study was conducted about gender differences in sexting, the sending of sexual explicit messages or images by cell phone. A researcher believes that the proportion of girls texting is less than the proportion of boys texting and decides to collect data in the spring of 2010 among a random sample of middle and high school students in a large school district in the southern United States. The researcher finds that 156 out of 2,169 girls are sexting and 183 out of 2023 boys are sexting. Is there enough evidence to support the researcher's belief that the proportion of girls texting is less than the proportion of boys sexting? Test at the 0.0 level of significance. So right away, just because right here they kind of make the claim here, they say, is there enough evidence to say that the proportion of girls is less than the proportion of boys? So I have a tendency of, because they mention the proportion of girls first, to write that first, I'm nearly just translating straight from the words straight into a math sentence, right? The shorthand math version, right? So see how it says proportion of girls. So if I write that as shorthand, then that is P sub girls, right? I'm not going to write out the word proportion. I just write P sub girls. That's proportion of girls, right? Is less than. So that means that I'm going to be, if something is less than, it's smaller than. So the alligator's mouth is going to face away from that smaller than value. It's smaller than or less than the proportion of boys sexting. So the P for this proportion here is the P here, and then of boys, so we say sub boys. So this is normally, because the girls are listed first, that makes me want to think that that's what we would say population 1, which it is, which listed in the null alternative hypothesis. That population is listed on the left, and then we'll also find that that's population 1, X sub 1, and N sub 1 are going to be girls. So population 1 here, because the girls' population is listed first or to the left in the null and alternative hypothesis, that actually the girls is our population 1 when they're talking about when we enter this into the calculator. So population 1 is girls, okay? And then population 2, that's the one that they list second, like right here. This is population 1. That's the one listed to the left in the null hypothesis, and population 2 is listed to the right in the null hypothesis. So population 2 is the boys. Okay, that's something important here, because when we go and they're like, what's X1, what's N1, what, because they use, in the calculator uses sub 1, right? And they have X2, N2. Well, to know what sub 2 means, we have to know what population 2 is, okay? So, so that's the big things here. We need to know what X1 is and N1 is and X2 and N2. And basically we find those out. And if you can correctly identify those, then you could probably correctly put it in the calculator and you'll probably get this correct answer. So first of all, they said the number of girls in our sample, that is the 2,231, I think. No. That's the 2,169. That number, is it less than 5% of all the girls in middle school or in a large school district in Southern California? Most likely. Like I said, they don't give us all of the students or all of the girls in this large school district in Southern California. They don't give us all the girls, but there's probably a lot of girls in a large school district. There probably is. And so 2,100 is probably less than 5% of all the girls in that school. I mean, there's probably 3,000 girls in just one high school alone. Let alone like the middle schools, you know, and they probably have, you know, 10 high schools, and and they have, that's all the middle schools as well. So I think it's a good idea. We're most likely with it, our sample sizes are, you know, less than 5% of the entire population. So we say yes here. Next, we actually have to check this next one. And let me clear all my drawing so far. We do have to check. So the in sub girls right there, that is the sample, the number of girls that were sampled. So that is this, the researcher finds that, okay, so 2,169 girls. 2,000, so plugging in for in sub girls, I'm plugging in 2,169. In for P hat, you're like, how do I find P hat? P hat for the girls, they don't put it there, it's just too tedious, I think. But P hat for the girls is going to be the X1 over N1. So the number of people who were sexting, that's the characteristic of interest, who they tested positive, if you will, they were, if you want, or they were a success. So we went and we asked 2,169 people, do you sext or whatever, you know? And people that said yes, we call that a success. So base X1 is the number of successes, the number of people who had the characteristic we were looking for. So that's 156 out of the 2,169. Oh, oops. Why do I have my comma? Usually calculators never want to put a comma in, just for our sake. Okay, and then, so we can put that in. We're going to multiply 2,100 and then multiply by 156 over 2,169 times by 1 minus 156 times 2,169. And we have to put all that into our calculator. And so I do. Let's double check that. And let's look at how that looks. Where's our information? Okay, so okay, I have that information. Okay, that makes it easy. So I just have to copy what I have written on there. 2,169 times by 156 times by 1 minus 156 over 2,169 and end it. Make sure you put the 1 minus in parentheses. So not all calculators will interpret that, but okay, that's a very large number. 2,169, 156. So that's definitely bigger than 10, right? Because this is saying, is this value, whatever n times 1, p times 1 minus p, is it greater than or equal to 10? And the answer there is yes. And so they do, whoa, we got a way different answer than us, though. What in the world? N of girls times P. Yeah, they get a very different, is it calculating it correctly? I will have to look into that. 2,169. Oh, I forgot. I didn't put divided by. Look at me. 2,169. There we go. So 144.8 is for 1 decimal place, because the 1 decimal place is 7, but you have to look to the right and ask, is it greater than or equal to 5? And it is. You add 1 to the 7, so you get 144.8. So there you go, 144.8. All right, and then you do the same thing with boys. The number of boys, and let's use blue. I feel like these in blue. And doesn't want to change colors for me for whatever crazy reason. Okay, maybe if I have to, all right, so then I'm gonna plug into this equation right here. So the n, oh, oops. Okay, n, the p hat for boys is the x2 over n2, which is where is it? The boys' information. So 183 out of 2231. 183 out of 2231. Okay, so then if I plug that in, then I get the boys is the number sampled in boys is 2231 times 183 over 2231, all times 1 minus 183 over 2231, and then I do that calculation. So I have to, all right, so I can input 2231 times 183 divided by 2231 times 1 minus 183 divided by 2231, and oops, I don't want that in the denominator. And then I get 168, and I actually, okay, so I'm gonna be, taking, I want one decimal place. So I look at the 8, I look to one place to the right of one decimal place, and then that's greater than or equal to 5. So I add 1 to the 9. If I add 1 here on the top to the 9, then that becomes 10, and then I would carry the 1 here to 8. So 168.0, or just 168 is the number we want here for this problem. And oops, wrong. Okay, 168. There we go. All right, let's clear all of the drawings. Okay. All right, so next, next determine the null hypothesis. And I kind of already, I told you guys, write out, we listened to it again. Is there evidence to support? So this is their claim that the proportion of girls, so P of girls, right, is less than, right? Something is less than, then it's smaller than. So the alligator's mouth is going to be pointing in the opposite direction of that smaller than thing. The proportion to P there is the proportion of boys. That's the alternative hypothesis. So the one we want here is less than. And then the null is always, it's always opposite of what the alternative hypothesis is. So really you identify the alternative hypothesis and then you identify what the null hypothesis is. But the null hypothesis, some people always just say it's always equal, just let it be equal, because equal is sort of opposite of what strictly less than is. So you sometimes they will accept equals, and almost equals is fine, answer right here. Or once in a while they'll say equals and the opposite inequality that you see in the alternative. So it might be equals, or they might also, they don't even like accept any like greater than or equal sign. So it's got to be equals here. So notice how when we look at this, they don't give us the opportunity to have less than or equal to symbol, right? They don't even have that symbol. So it's got to be equals in the null hypothesis here. All right, the next thing is the hypothesis test is, now whether it's right tail, left tail, you just look at the direction. See the alligator's mouth or the inequality symbol, it looks like a arrow. So it's pointing, that arrow is pointing to the left. Yes, it's pointing to the left. So that would make this a left tail test. So we would choose left tail test here. And then now we just have to determine the null return hypotheses. And I erased it. We had everything up here so nicely. Whatever, I'll just put it again. Okay, X1 was, population 1 was the girls. So X1 is the girls, 156. And N1 was 2169. X2 was 183, and N2 was 2231. And so now I have all my information. Now I can run my hypothesis test and find the Z and P at the same time. So let's do this is a proportion, independent proportion 2 sample test. So I go to stats, tests, and then I go to 2 prop Z test. And then all it wants is the information from my sample, 2 samples. So the X1 here, we said the population 1 because it was listed on the left in the null hypothesis, right? It's listed right here. Notice how it's the girls' population is listed left on the left, and then the alternative hypothesis. So that is my population 1. So I come over here and I put X1 is 156 and N1 is 2169 because that was the information from the girls. And then now the information of the boys, 183 and 2231. And it gives me all 3 p-values for all 3 types of hypothesis tests that I could do. I am doing the left tail test, am I not? We just decided we're doing a left tail test, and I just showed you which direction. So yeah, it is, the arrow is pointing to the left. So there's a left tail test. So I just need to choose the arrow pointing to the left. That is the p-value I need. So it's right here. So my p-value is 0.1044. So, and the test statistic is negative 1.25. So just so that you know what's going on here, in a 2-tailed test like this, they basically subtract the 2 sample proportions. They subtract the 2 sample proportions. And and they also find the number of they find the z-score of that, which is the number of sample standard deviations away from the mean. The mean here in a difference problem like this, or you know, like in a 2 sample problem like this, the mean of the distribution is 0. And so the Z distribution is saying there's 1.25 standard deviations below the mean. That's where this sample is located. That's where, so like the empirical rule tells us that 95% of the data is within 2 standard deviations. So what the idea is outside of 2 standard deviations, everything else out there is unusual. Well, this is saying this is only 1.25 standard deviations below the mean. So I would not say that this is very unusual, not really, but it does happen 0.10 times. So out of the probability of it happening is 0.10. So it happens 10% of the time. So it's not that unlikely. So that sample, or the differences between those samples is when in the distribution of all the differences of samples that could possibly take place. This one is 1.25 standard deviations below the mean. So, and the probability of getting that like that would be, we put our Z, there's our Z test statistic here. And this is our p-value underneath the area underneath the curve here, and it's equal to the 0.10. So that's just if you were interested in figuring out, 4469 or whatever it is. Understanding what the p-value is, the probability of me getting two samples with such different p-hats, given that we thought that they were coming from the same population with the same proportion, how common and how common is it to get a sample that are so are so different from each other, have such different p-hats from each other proportions. So that is that is the picture that goes along with this particular problem. So let's all finish off the problem. So our p-value is 0.10. 0.10. Yeah, to 4 decimal places, 0.104. 0.104, and let's just double check that I got exactly the same answer as them. 0.104, and then yes, I would have rounded to 5. So I get exactly the same answer as them. Oops, sorry. All right, and then now we look at the level of significance here. I was talking to this with another student. I'm like, what is the level of significance? What is the level of significance? Alpha is really, we make a choice here. How unusual is too unusual, right? We're gonna say if something is so unusual, then we're going to reject the null hypothesis. But you have to draw that line about what is too unusual. And that unusual, what is too unusual, that is subjective to everyone. Like, I feel like that was, I don't think that's so unusual to me. Like, so it's unusual to everyone. It's like if I was doing sweetness tests, right? Let's say that I was like, I owned a bakery and I'm trying to make sweets. And so I ask a girl like, is this too sweet or something like that? It might be a good idea for her to say, well, anything that has more than 1 cup of sugar, that's per recipe or whatever, that's too sweet for me. And that would make it really easy for me to go through all of my recipes and say, hey, does it have more than 1 cup of sugar? If it does, I'm going to say it's too sweet and I'm getting rid of it, that recipe. So that 1 cup of sugar, that is a good cutoff for me to judge what is too sweet and what is not too sweet. And that's what the alpha and the level of significance does for us. It draws a line in the sand that says anything more unusual, anything more unusual than this, we're gonna reject the null hypothesis because it's so unusual, okay? It draws that line for us because what is too unusual, that's too subjective, that's different and for everybody. So this is what it kind of looks like. We just focus on it like this. Our p-value is 0.10 and our alpha, the test level at the 0.01 level of significance. So our alpha is 0.01. So our alpha makes that cutoff. This is a regular number line, zeros over here. I'll make this 0.01, right? The alpha makes that cutoff point where anything smaller on the number line, and this is like 1 whole over here, anything smaller than alpha, let me make a red, I like the red. This is our cutoff point. There's the alpha. Anything lower, we're gonna say is unusual. Unusual, okay? And then anything higher than alpha, we say it's not unusual. And if we say it's unusual, we say it's statistically significant. Because statistically saying, we can make some real bold statements about it. If it's not unusual, not unusual. Or let me put this is my blue region, so I'll write. If it's not unusual, then we don't reject the null hypothesis, you know? Okay, so anything between that's lower than alpha, anytime we have a test statistic or we have sample data and we use that sample data, plug it into the calculator, and we get a p-value, and that p-value is less than alpha, then we say it's unusual, we reject the null hypothesis. So in this red region, sometimes they call this the critical region, or in this red region, we reject the null hypothesis. Anything larger than alpha, we would actually, I think equal to alpha or larger than alpha, we just say, hey, we failed to reject the null hypothesis, okay? All right, so hopefully you understand that a little bit better. So I'm going to say, because, we never actually, so I have 0.1 and alpha is 0.01. So how do I compare those? Well, 0.1 is over here. It's in this not unusual area because 0.1 is larger than 0.01. However, if you weren't sure about that, let's look at that a little more closely. This is 0.01 point alpha, and that's 0.01. Oh, I'm sorry. I'm getting these mixed up, dear. This is our p-value. This is our alpha. How do I compare those two? This is like saying I have 1 dime and 0 pennies. This is like saying I have 0 dimes and 1 penny. Which one's bigger? Well, having 1 dime is bigger than having 1 penny. So the p-value is bigger. Another way, if you're concerned about how to compare these two decimals, is you could make sure that they add any extra decimals you need to, so they both have the same number of decimal places. Then drop the decimal completely and just think about it as 10 compared to, and drop any preceding zeros. 10 compared to 1. 10 is larger than 1. So 0.1 was larger than 0.01. Okay. So the p-value is larger than alpha. I failed to reject the null hypothesis here. And then the last, now, if I fail to reject the null hypothesis, I always fail to have enough information, to have enough evidence. Or I say there's not sufficient evidence. So that's why I wrote this last here. There's not sufficient evidence to support the claim that they were trying to claim, right? Which is the same as the alternate hypothesis. All right, well, I hope that listening to this video helped you understand this a lot more deeply. And please email me if you guys still have any questions. Okay, bye.